So yesterday we saw some quadratics that were not manable. Something in the form of f of x equals ax squared plus bx plus c. So if something is not manable is the best way to do it, right? Because it's efficient. But you will run into questions where you can't man it. Or even if you could man it, the numbers are too big and you could be sitting there like doing this for like ages. So something that always works is the quadratic formula, which looks like this. X is minus b plus minus b squared minus 4ac over 2a. This is a very important formula used basically. I don't know if you'll be doing this in grade 9, but you will see this soon. Maybe even in grade 9. I saw it in grade 8, but I was in a different country. Anyways, so how do you use this? So let's do a quick example, right? It just looks intimidating. It's not that bad. So y is equal to, let's say it's 2x squared plus 3x plus 4, okay? Compare this with this, ax squared plus bx plus c. What is a, what is b, and what is c?
A is 2, B is 3, and C is 4.
Well, easy as that. Now we're going to plug it into this formula. So this will give you the x-intercepts straight up. So it's going to be minus b, so minus 3 plus minus 3 squared minus 4 times a is 2 times c is 4. All over 2 times a is 2, like that, okay? So you get negative 3 plus minus 4 times 2. Well, this is not going to work out actually, because we're going to get a, let's change the b to something a little bit bigger. Let's change it to, what's 4 times 2? 8 times 4, 32. Let's change this to 6. Otherwise, it's not going to work out here. And I'll tell you why in a bit as well. So b is now 6, and then we have 6 squared minus 4 times this. So the next step would be to just do this. So 6 squared is 36, minus 4 times 2 is 8. 8 times 4 is 32. Like that, right? And then you get a square root of 4, which is a 2. So this entire square root bit is just simply a 2. So we can erase this, replace that with a 2, and on the bottom we have 4. And whenever you get this plus minus guy, all you need to do is you need to split it up. So this means either it's going to be negative 6 plus 2 over 4, or it's going to be negative 6 minus 2 over 4. So this is negative 4 over 4. One of the x-intercepts is at negative 1. This one, negative 6 minus 2. Another one is at negative 2. And there you go, okay? Does that make sense?
Mm-hmm.
Quadratic formula. Usually you'll be given this when you first see it, I guess, but eventually you're expected to memorize this. And this is bulletproof. What does this mean? This means if there's x-intercepts, this will always work. You don't have to be able to factor it, okay? If you can't factor, which means you can't man it, you're going to use the quadratic formula.
Okay.
What does it give us? What do these represent? Negative 1 and negative 2. That is the x-intercepts, okay? So
Mm-hmm.
this is a parabola that opens upwards. The y-intercept is 4. And we know the two x-intercepts, one of them is at negative 1 and the other one is at negative 2. And then it's going to look something like this. There we go. This vertex, there's a way to find this vertex. The way to find the vertex, we don't, let's not worry about that. We've done this before, so the important part here is the x-intercepts. Okay, so they give you the x-intercept. Here, look at this graph. It's a degree 2 polynomial. It's a quadratic. What are the x-intercepts? So x-intercept is when it touches the x-axis. Does it touch the x-axis ever?
No.
No, so it has no x-intercepts. Okay, graphically, that's how you can tell if something has an, again, it doesn't necessarily have to have x-intercepts. Degree 3 has to have because it crosses it. But degree 4, degree 6, all these guys, they don't have to have x-intercepts. So that's the graphical way, right? But how can we deduce algebraically that it won't have a x-intercept? And this is how you do that. That was the question that we had before. 2x squared plus 3x plus 4. A is 2, B is 3, C is 4, right? If you compare this with this. Now let's try plugging this in the quadratic form and see what we get. In fact, I'm only interested in this bit here. So we have the square root of b squared, so that's 9 minus 4 times a is 2 times c is 4. So we have 9 minus 32, so that is negative 23. What's the square root of negative 23? Any ideas? Square root of negative 23. What does it give you? If you plug it in a calculator, what does it give?
It says error.
Right. So again, if you think about what a square root actually means, right? Here, let's pick an easier number, right? Square root of negative 4. We know the square root of 4 is 2. So which leads you to thinking even this one's going to give you an error. So you may think it could be negative 2, right? But negative 2 times negative 2 is positive 4, not negative 4. So the idea is you can't take the square root of a negative number, okay? It does not exist. For our purposes, it does not exist. So that means this equation here doesn't have any x-intercepts. It will never touch the x-axis. And you can just find that by this bit here. See this b squared minus 4ac? If that number is negative, then you will not be able to take the square root of it. So that means the x-intercepts don't exist. 2x squared plus 3x plus 4. What does that look like graphically? Boom, you see? It'll never touch the x-axis. Graphically, it's easier. You just look at it. But algebraically is a little bit more difficult. Well, it's not that difficult. You just plug it in to find your a, b's, and c and plug it into that. There's 3 conditions to know how many x-intercepts something has. You see this bit, the b squared minus 4ac? Just this bit in the square root. If this is less than 0, what does less than 0 mean?
Negative numbers.
Yeah, exactly. If that bit there is a negative number, then there are 0 x-intercepts, no x-intercepts. If that bit there, we can call this something. It's called the determinant because it determines how many x-intercepts something has. B squared minus 4ac, if this is exactly 0, right? If this is exactly 0, this means it has 1 x-intercept. And if that thing is greater than 0, any positive number, then it has 2 x-intercepts. And it can only have a maximum of 2 x-intercepts because it's a degree 2 polynomial. Okay?
Okay.
So this bit here is the guy that tells you what's going on with the quadratic. And this formula always works. As long as there's an x-intercept, it always works. You don't have to man it. Manning it is obviously easier, but sometimes you'll never be able to get it, right? What if it multiplies to like 10.86 and it adds up to like 4.3? What are the numbers? Well, who knows what the numbers are? There's like so many combinations. So when you get something like this, you want to use the quadratic formula. And if there are x-intercepts, you can quickly check by just doing this. You'll be able to find them. Okay?
Mhm.
So that's a bit about quadratics. Let's try doing this. Now they've given us something on a number line, okay? And our goal is to turn this into an inequality. Here, I'll do the first one. It's very simple. Open circle means it's not inclusive. So it's going to be strictly less than or greater than. The fact that it's going right, it's becoming bigger and bigger. This is simply x is greater than 8. 1 and done. What do you think the answer is for B?
X is greater than -4, but it can also be -4.
Yeah, so it's greater than or equals to -4, right? Easy as that. What about C?
X is greater than or equals to -24. I mean -12.
Less than, because it's going left, right? Less than equals. What about the last one?
X is between -9 and -1.
Now look at the notation here. X is greater than -9, right?
Mm-hmm.
But it's less than -1, and it's not inclusive because there are open circles there. Here, let me show you how to do this in the interval notation, which is what I prefer. It looks like this. So we're going from, again, we're going right from 8. So 8 is not inclusive, so it's going to go from anything from 8 to infinity x can be. For the second one, it's going to be anything from 4 to infinity, -4, but it's inclusive. That's why there's a square bracket there, right? What do you think the answer is for C? It's going to be between something and something. So if you keep extending this number line, you'll get to -infinity on the left, yeah?
Mm-hmm.
You always have a lower bound and an upper bound. So for C, the lower bound, x can be anything from -infinity to -12. Inclusive means a square bracket, right? What about D?
Um,
Well, because there's no equal.
-9 and -1, but you wouldn't put the square brackets.
No, not square, the normal bracket, rounded bracket. Square is when it's inclusive. Closed
Okay.
circle is when it's a square bracket. Let's try doing one or two of these guys. For B, what's the first step?
Multiply by 5.
Yes, so if you multiply by 5, what do you get on the other side?
Do I multiply everything with 5?
What do you think?
Yes.
So you're going to be doing this times 5. So what do you get?
So 10x plus 15 over 10.
No, over 2, okay? Because you see that 5 is in the numerator here. It has an invisible denominator of 1.
Oh, okay.
Okay, like for example, 3 over 2 times 3 is 9 over 2. Because if there's no denominator, the denominator is 1. Do not multiply everything by 3. In contrast, though, if you have something like 3 over 2 squared, now this squared applies to both numbers. It will be 9 over 4. When you're multiplying by a number, just multiply the numerator with the numerator, denominator with the denominator. There we go. That's the first step. What would you do next? There is only one thing you can do.
Multiply by 2.
Yes. So you'll get 2x minus 8 on the other side. Now notice how the like terms are not on the same side, so you need to move things around a bit.
Could you add 8?
Yeah. 15 plus 8 is 23.
And do you divide by 2?
No. You need to put the like terms on the same sides.
Could you subtract 10x?
Yes. So you get negative 8x is 23. You divide by final step, you divide by negative 8, but the sign flips. And that's going to be the final answer there. Okay?
Mm-hmm.
Easy as that. What about C?
You subtract 2.
From both sides? All right, let's do that. So you get negative x, x minus 4. Now what? You can notice how the like terms are not on the same side. By like terms, what are like terms? Like the numbers, the letters, right?
The
X's.
x's.
We need to bring the x's to the same side.
Do you subtract x?
Yes. So subtract x from both sides. This one and this one cancels out. Then we have negative 2x is greater than negative 4. And then just divide by negative 2, flip the sign, 1 and done. Here they were nice enough to factor this for us. What's the degree of this polynomial?
Degree 3.
Is it opening up or down?
Down.
Yes. So there's two ways to do this, right? We can do the graphical way first. Where are the x-intercepts?
1, -5, and 7.
Not negative 5, try again. Not negative 5.
-5/2.
Yes, which is negative 2.5. It's a degree 3 polynomial, but at the leading coefficient's negative. It's going to start in Q2 and in Q4. We don't really care what the y-intercept is, I guess. The only thing that matters is the x-intercepts. Boom. Nothing fancy going on, right? It's going to go through here. Looks like the y-intercept is going to be negative. You could find the y-intercept by making x as 0. So what will that be? Negative 2 times this is just 2 times 5 times negative 7, 10, negative 70 would be the y-intercept. But you don't need that to answer this question. Does look good on the graph though. So greater than 0 means it's positive. Where is this function positive?
Um, when x is less than negative 2.5,
Less than or less than equals to?
less than equals to.
No, it's only going to be less than equals to if it was like this. Okay?
Oh, okay.
Because we want strictly positive. We want strictly positive. If it was exactly 2.25, then it would be x would be 0. Sorry, y would be 0. Y can't be 0. We need y. This entire thing is y or f of x. We need it to be strictly positive. So that's why this is going to be x is strictly less than negative 5 for y to be positive. Where else is it positive?
When x is between 1 and 7.
Right, so when x is between 1 and 7. Right, that's one way to do it. If you want interval notation, the first one would be from negative infinity to negative 2.5 exclusive. The other one's going to be from 1 to 7 exclusive as well. If you have multiple intervals like this, what you can do is you can just write u there. U just means and. All right.
Mm-hmm.
U in math means, well, it means union, but it just means and for our purposes. The other way to do this is the algebraic way to do this, for which we need to find the intervals. So to find the intervals, we're going to plot a number line, and we're going to plot our x-intercepts. So this is going to be our first interval, negative infinity to negative 2.5, negative 2.5 to 1, 1 to 7, and 7 to positive infinity. So those are our 4 intervals that we need to check for. And over here, all our factors go in here. 2x plus 5, x minus 7, and negative 2. Like that. Well, negative 2 is going to be negative 2 everywhere because it doesn't have an x guy attached to it. And then we want to pick a number and plug it there as x. For this one, I'm going to just plug in negative 10, I guess. Negative 10 minus 1, negative. 2 times negative 10, negative, plus 5, negative. Everything is negative. What do 4 negative signs make?
Positive.
Positive, exactly. Pick a number between negative 2.5 and 1.
Negative 1.
Pick a 0. 0 is way easier. You could pick negative 1. That's not wrong, okay? Because if you pick a 0, you can just ignore the x's. This is going to be negative because of the negative 1. This is going to be positive because of the positive 5. This is going to be negative. So we have triple negatives and a positive. What does that make?
Negative.
Yes. And now from here, it's just a matter of picking 1 and 7. I'm going to pick not 5 because it's a nice number. Positive, positive. 5 minus 7, negative, makes a positive. 7 to infinity, you can pick 10. So positive, 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 and then negative here, you see? So what did we want? We wanted it to be greater than positive. So one of our answers is right here. Because this is positive, we go back up here. Negative infinity to negative 2.5, and the other answer is right here. 1 to 7, and that's what we had here from the graphical approach. Both of these are going to be the same. The answers will be the same, okay?
Okay.
But it's important to know how to do it this way because so far we've been dealing with polynomial functions, which are a little bit easy to graph. The next chapter is gonna be something that's a little bit more difficult to graph. So maybe in that case, you don't want to be using the algebraic approach. I'll show you what I'm talking about. This is called rational functions. So we've never done something like this, but it's similar to polynomials. The only difference is maybe you have a polynomial on the top, but you also have a polynomial on the bottom, something like this. This is called a rational function. Okay?
Mm-hmm.
something on the top, something on the bottom. And here, look at this. If x were to be, let me give you an easier one, okay? 1 over x minus 1. Let's say x was 1. What's the y value? Got an error? Did you?
Uh-huh.
Do you want to know why you got an error? Here, let's see. We have 1 divided by 1 minus 1. So we have 1 divided by 0. What's 1 over 0?
It doesn't really work.
It doesn't work, right? Yeah, so this is, you can't divide, you can't multiply by 0. You can have a 0 on the numerator, but you cannot have 0 in the denominator. You cannot divide by 0. 0 cannot be your divisor. Okay?
Mm-hmm.
So when that happens, we're gonna get a little bit technical here. When that happens, this is something called, we've done this for exponential functions. This is called a vertical asymptote. For the exponential functions though, like for example, y equals 2 to the power of x, we didn't have a vertical asymptote. We had a horizontal asymptote, like right here at y equals 0. Because the asymptote is given by the d value that you add. If there's nothing, it's going to be 0. This one is called a horizontal asymptote. Asymptote just means a like an invisible wall, like an invisible barrier. Okay.
Mm-hmm.
So for exponential functions, it would have had a horizontal asymptote. Polynomial functions doesn't have any asymptote. But a rational function has both a vertical as well as a horizontal asymptote. Here, let me quickly show you what the graph of this looks like. So x cannot be 1. We've decided this, right? If x were to be 1, then we get 1 over 0, which is what? X cannot be 1. This function has a very strict restriction. So that means what x cannot be, 1, there's going to be an invisible wall like this. So our function will never cross this barrier. In fact, it also has a horizontal asymptote, which I'll tell you how to find in a bit, or you can just kind of decide it. What's the d value here? What are we adding to this? We're adding a 0, just like here. The d value is 0, so that's always going to be a horizontal asymptote. And the graph of this looks like this. Don't worry too much about it. But the point is, like, it's very difficult to know what the graph exactly looks like. So maybe in that case, the algebraic way will be more efficient. See? This is the first one anyways. This is the basic one, 1 over x. Eventually you could have something like this, where you could have like multiple asymptotes, right? You could have something like this, that. There we go. And coming up with this sketch is going to be very difficult. So maybe at that point when you're trying to solve an inequality, maybe the algebraic way is more efficient. Here, let's do a quick thought experiment. And I'll show you how I got those graphs. We're gonna try and sketch y equals x. Okay. How do you sketch this? This is a linear function. How do you sketch a linear function? Where's the y-intercept? No? Here, I'll help you. Look at this. Compare this with this. What's our b? What's our y-intercept?
0.
0, right? What's the slope?
1.
1, right? So for every positive 1 means for every 1 unit you go up, you go 1 unit to the right. You see right there. To plot a linear function, you just need 2 points, and then you just connect the dots and you extend them indefinitely like that in both directions. There you go. That's the graph of y equals x, okay? In other words, y equals 1x plus 0 if you wanted an mx plus b form. Now, using this, okay, let me just count. 2, 4, 6, 8, and let's say this here is 100 for our purposes. Same thing down here, 2, -2, -4, -6, and say 100 is down here somewhere. So that's to scale, but it's just to make a point. Now we're gonna try and graph y equals 1 over x. Now, how does that work? You see this? There's an x value of 1, yeah?
Mm-hmm.
So we're trying to plot 1 over x. What's 1 over 1?
1.
1, right? So for our reciprocal function, this is called a reciprocal function because it's flipped. X was on the top, now x is at the bottom. So when x is 1, y is 1. What about when x is 0?
Then you get nothing.
You get nothing, right? You'll get a vertical asymptote because you'll be dividing by a 0, right?
Mm-hmm.
So that means that exactly when the x value is 0, we have an invisible wall like that. What about when x is 4? What's the y value? Again, this is our function, 1 over x.
You would just get 4.
No, 1 over 4. 1 over 4. Right? It'll be 0.25 or 1/4. This is our
Mm-hmm.
function y equals 1 over x. We want to know when the x value is 4, what's the y value? Just plug 4 in here. So you get 1 over 4, you get 0.25. So when the x value is 4, the y value is 0.25 here. Cool?
Uh-huh.
Now let's take an arbitrary point. When x is 0.01, what's going to be the y value? It's the same function. You can use a calculator if you want.
You get 100.
Exactly. So 0.01 would be somewhere here, right? Somewhere here. So you get 100. There we go. And now you just connect the dots. Goes from there, and then we had this point here. We had this point here, and it's never going to cross that because it also has a horizontal asymptote. That's the 1/2, right? Now, if you notice, what's the y value when x is -1? Well, 1 over -1 is -1. So this point stays right there. See that?
Mm-hmm.
Now we're interested in Q3. There's not going to be anything in Q4 or Q2. When x is 0 already completed, when x is -4, you would have 1 over -4, which is -0.25. So when x is -4, you have 0.25. And when x is -0.01, you have a -100. Then you just connect the dots. There we go. Now we've graphed 1 over x. Okay?
Mm-hmm.
Now let's see what they want us to do actually. Okay, they want us to graph this guy. 2 minus x. Again, it's fairly simple. It is not that difficult. Let's see. To graph this, we would first need to graph this guy right here to graph the reciprocal function. So what's the y-intercept? What's the slope? It's a linear function, 2 minus x. What's the y-intercept? What's the slope? No? What if I wrote it like this? What is our m and what is our b?
The y-intercept is 2.
Yeah? M is -1. Was that difficult?
No.
No, right? We're just graphing a linear function. So far, it should be pretty straightforward. Yeah, they will give you the order like opposite, but that shouldn't make a difference. The slope is always a number that x is being multiplied to. In this case, 1, -1. Anyways, so how do you graph a linear function? We're gonna start at the y-intercept of 2, and now the slope is 1. So instead of going up and right, we're gonna go down and right. So go down 1 unit, go right 1 unit, okay? There we go. And you just need 2 points. Then you just connect them that direction, and you connect them. Yeah, that's looking good. Straight line, yeah. There we go. That's the graph of y equals 2 minus x. Cool.
Mm-hmm.
But the goal now is to graph 1 over 2 minus x. Tell me, what value of x would give you a 0 in the denominator? See here?
2.
2, exactly. So that means when x is exactly 2, we get a vertical asymptote because that's going to give us a 0 in the denominator. We can't divide by a 0. So when x is exactly 2 right here, we're going to get an invisible wall that we can't cross. See, like that. Again, now for the rest of them, I'm going to just draw like a mini table of values. When x is 1, what's the y value for this function?
It's 1.
It's 1, exactly. What about when x is, let's see where this is going, -100? You'll get 1 over 2 minus -100, right? So 1 over 2 plus 100, it's going to be 0.00 something, okay?
Mm-hmm.
So when x is -100, our y value is going to be a very small 0 point something, way, way below the 1. Similarly, what about when x is 1.99? What about when x is 1.99? What's the y value?
It's 100.
Yeah, it's 100. So 1.99 means right here, next to the left of 2, we'll go all the way up there, 100, and then we're going to connect the dots, right? So where did this go? This went through this 0.00 something, went to 1, and then when x is 1.99, it goes to 100, like that. And it's going to keep going. Okay, it's going to keep going. It'll never pass that. It's going to go upwards towards infinity. Now, all these reciprocal functions, they're all symmetrical per se. What do I mean by that? They kind of behave like odd functions. They're diagonally mirrored. Like odd function is something like this, or like a linear function is also an odd function, or a cubic function is also. Whatever you have down here, you'll have up there, or like here and here. It's symmetric about the origin. Well, that's the definition of an odd function. It's symmetrical about the origin. But this one is symmetrical around the vertical asymptote. Okay? Or you can always pick points, right? You can always pick points. Let's say when x is 3, what's the y value?
-1.
-1, right? So when x is 3, that's 3. We have -1. You see that point? What about when x is 2.01?
It's -100.
Yes. So -2.01. Sorry, 2.01 means just to the slightly to the right of 2. 2 is where the red dotted line is. So 2.01, it's going to be -100. Again, that point doesn't matter. It's going to be somewhere here. Using the same logic, when x is 100, y is going to be 0.00 something. So when x is 100, let's say that's 100, it's going to be right there. And then you connect the dots. And there we go. That's the graph. That's a reciprocal graph of 2 minus x. Okay. Yeah, but to graph that, you need to know how to graph the linear function. All right, what about now? Let's take this up a notch, right? Let's take this up a notch. So far we've done linear functions. Now let's do the reciprocal of a quadratic function. Again, not much changes. The logic is the exact same, but again, you need to be able to graph the degree 2 polynomial. I'm going to rewrite this as negative x squared plus 9. So that means it's a parabola that has a y-intercept at 9, okay? Maybe we need to make a table of values, x, y. X is 1, y is 8. When x is -1, y is 8. When x is 2, -4, y is 5, -2, 5. So 1, 2, 3, maybe there. And you see the pattern. It's going to look something like this. Okay, that's our quadratic function. But now we are trying to graph, not this, we already have it. Trying to graph 1 over that, okay? 1 over that. Now the question to you, is there any value of x here which would make this equation true? What value of x would give us a 0 in the denominator? To find that, we're going to have to solve this equation. How do we solve this equation?
Subtract 9.
Yeah, so x squared is 9. What else?
U square root
Yeah, so the negative signs cancel out. U square root. What's the square root of 9?
3.
Try again. Only half, right?
3 and -3.
Yeah, plus minus 3. So that means we have a vertical asymptote at 3, okay? See right here? I didn't draw this graph right, but it's 3 should be right there. Boom, 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 boom. That's a 3. And then same thing here. That's a 3 for us. Boom, 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 boom. And there's always going to be a horizontal asymptote on the x-axis. So there we go. Okay, that's our setup. Now we just kind of plug and chuck the values. Look at this. This equation, when x is 0, what's the y value? For this guy here. Well, when x is 0, you can just ignore the 0, right? It's going to be 1/9, which is like 0.01. 0.11, actually. Okay? So for a reciprocal function, when x is 0, y is this. When x is, let's pick a nicer number. Let's say, what about when x is, what's a good number? 2. We have 1 over 5, which is going to be 0.4. -2 is also going to be 0.4. So for 2's, we end up here. See? And then you kind of keep plugging the points. So we know our asymptote is at 3. If you plug x as 2.99, you would get like 100. You'll go all the way up there. If you plug x as negative 2.99, you would get 100 up, all the way up there. And then you just connect the dots. Like that. Okay?
Mm-hmm.
But we're not quite done with this because this is only the reciprocal of the middle part. We have something over here and something over here. You can always plug in points, but see, that kind of looks like a straight line. It's going to look something like this. The reciprocal of a straight line is like a curve. And that's going to be the graph of that, 1 over negative x squared plus 9. Okay?
Uh-huh.
I could have always plugged in points right here. For this part, we could have always plugged like -5, where is it? -1, where is it? Then we would get this point and this point, and then we would just kind of connect them. Same thing here, +5 and +3.1 or something, and just connect them. So that's the graph of 9 minus x squared, the reciprocal of it anyways. See, like that. They also use a lot of like points, which is good, right? So this is the rule of thumb, right? This is the rule of thumb. Let's say n is the number of asymptotes. Then your graph, okay, will have n plus 1 sections. Now, what does that even mean, right? Like, for example, this quadratic thing that we had 2 x-intercepts, yeah?
Mm-hmm.
Then our graph had 3 chunks. We had 1 chunk in the middle, we had 1 chunk on the right, and then we had 1 chunk on the right. There we go, like that. In the previous question, so in this case, n is 2, so that means our graph will have 3 sections because 2 plus 1 is 3. In the last question that we did, the linear function, we only had 1 asymptotes, so how many sections does it have?
Only 2.
2, exactly. So we had 1 guy up here, 1 guy down there, like that. Now let's see if you're ready for this. It says match the graph with the equation. Let's kill the easy ones out, right? I see a quadratic, I see a linear function, I see a positive quadratic, I see a negative quadratic. Let's start off with graph C. Which equation could possibly be graph C? No, this one. It's just a normal degree 2 polynomial. Well, it's between D and E. Which one do you think this is?
It's D.
It has to be D, right? Positive leading coefficient. So C is D, confirmed, right? Now, where does it have, you see these? Where are the x-intercepts?
1 and -1.
Yes, so whenever the main guy has an x-intercept, the reciprocal function will have an asymptote, okay?
Mm-hmm.
So this one has 1 and -1. That means E must be equation B. You see this guy and
Uh-huh.
this guy are reciprocal functions, this one and this one. Because x squared minus 1 had x-intercepts at 1 and -1, that means 1 over x squared minus 1 must have x-intercepts at 1 and -1 as well. So that's how they're related. So B is done, D is done. Let's look at D. There's only one linear function. Which one could it be?
F.
Yes, this has to be F, right? It has to be F. Now, where does this one have an x-intercept? Approximately.
By 2.
Yeah, it's 2 point something, right? 2.5-ish?
Mm-hmm.
which one of the remaining graph has an asymptote at 2.5-ish? See this one here? That one, A.
Mm-hmm.
Okay, there's an invisible wall. Yeah, so the dotted line is for us. If you graph it on Desmos or something, it won't show you the dotted line. The dotted line is for us to understand, but it does exist because it's supposed to be technically an invisible wall. So that means F and C are related, right?
Mm-hmm.
C is a reciprocal function of F, so A must be C. Now we're left with F. This one, let's see this one. We only have two guys left, A or E. Which one is graph F?
E.
Has to be E, right? So that means, again, look at this. This one has no x-intercepts. Notice, graph
Mm-hmm.
V has no x-intercepts. So that means our reciprocal function has no asymptotes. Which one of these graphs don't have an asymptote?
E.
B, right? So B must be A, the reciprocal function of E. Did that kind of make sense?
Mm-hmm.
Let's see which one's looking dicey. I'm trying to find a dicey one here. Okay, this one. Let's start with this one. So don't worry too much. It's easier than you think, okay? Because we've done this quadratic, this man thing hundreds of times. Let's factor C. What does it multiply to? What does it add up to? What are the numbers? We're trying to factor this guy here.
It multiplies to -15 and adds
Yes,
up to 2.
-2. What are the numbers? No, just think of
Um,
only two things multiply to 15. One of them is 1 and 15. There's no way that adds up to 2. What's the other one?
is it 5 and 3?
Which one's negative?
5?
Yeah, -5 and 3. So therefore we can factor this as x minus 5 because the leading coefficient is 1, x plus 3. So where are the x-intercepts?
5 and -3?
Exactly. So the graph of this, again, we don't know where the vertex is. We don't really care. But we do know there's one at 5 x-intercept and there's one at -3. So the graph of this will look like this, right? This is our quadratic, correct?
Uh-huh.
Now look at this. For our reciprocal function g of x, wherever we have an x-intercept on the quadratic, we just draw an asymptote, a vertical asymptote, like this, okay?
Mm-hmm.
So therefore, the asymptotes would be at x equals -3 and at x equals 5. At the x-intercept, there's going to be a vertical asymptote for the reciprocal function. In order to sketch this, it's easier than you think. You just do 1 over all the y values. Now, what do I mean by that? You see, this is 15 for the main function. That means for the reciprocal function, it's going to be 1 over 15, 0 point something. This is -1, 1 over -1 is -1. This is +1, 1 over +1 is 1. And they just kind of connect the dots. And then because there are two asymptotes, our graph will be divided into 3 parts. You see this one has a y value of 100. 1 over 100 is 0.01 down here. This one maybe has a y value of 5. It's going to be here. 1, it's going to be there. Boom, like that. Let me explain it to you in detail. Now look at this. Let's say the y value here is 100, right? For the main function. That means for the reciprocal function, it's going to be 1 over 100. Reciprocal just means flip it upside down. So that point for the main function becomes 0.01 for the reciprocal function. Let's say here, for the main function, the y value is 1. For the reciprocal function, it's going to be 1 over 1, which is still a 1. So that point doesn't change. Let's say for the main function here, the y value is 0.01. So for the reciprocal function, it's going to be 1 over 0.01. It's going to be 100. So this 0.01 for the green main function becomes the point of 100 for the reciprocal function, and you just connect the dots. And there we go. We've graphed this one.
Okay.
Looks kind of fancy, doesn't it?
Mm-hmm.
Looks very interesting. But yeah, that's how you do this. It looks difficult, but it's if you just use logic, then it ain't so bad. Here, let me show you one more. This one's a fun one. So it basically tells us to sketch the reciprocal function. We don't care what this is. This is actually a semicircle, okay? But we don't care about the equation. We're just interested in the graphs. Again, look how easy this is. Whenever there's an x-intercept, our opposite guy is gonna have an asymptote. Okay, like that.
Uh-huh.
And then you just take the y values and then you do that. Your y value is 6. What's 1 over 6? 0.15 or something? That's gonna come like here. Use a different color, maybe here. What's the y value here?
4.
4. So it's gonna be 1 over 4. It's gonna be 0.25, right?
Mm-hmm.
So so that point is gonna drop. It's gonna be slightly above 0.15. Same thing on the other side. Here it's a 4. 1 over 4 is 0.25. Here it's 2. What's 1 over 2? 0.5, right?
Mm-hmm.
0.5. When it's 2, it's gonna be 0.5. And look at this. Over here, it's like 0 point something, 0.01 for the main function. It's gonna become like 100 for the opposite function. See that?
Uh-huh.
Same thing on the other side. Here's 0.01 for the opposite function. It's gonna be 100. And then you just nicely connect the dots. So boom. It's not perfect, but you know what I'm trying to do. And that's the graph of the reciprocal function. Looks like, I don't know, like a U, like a fat U at the bottom. Okay?
Mm-hmm.
All right, let's call it a day there for today. All
All right. Thank you.
right, see ya.